Yep, I can imagine you waking up this morning and wondering, oh, I can't go on, I have no idea what a quadratic is. Well, hopefully we will sort that out in this very short video. And this topic is going to be split up into quite a lot of short videos. Keeps your attention span if nothing else. And so we will make it begin. What is a quadratic? Well, by the end of this video, hopefully you'll have learned some of the important language that relates to curves, obviously what the word quadratic means, maximum, minimums, turning points, and a little bit more. So what is a quadratic? Quad, well actually quad generally means 4, but in this particular instance I'm going to tell you now that it has absolutely nothing to do with the number 4. We know that for straight lines, graphs can be written in the form of y equals mx plus c. We've done lots of that at the moment with regards to the graphs we've been working on in previous sections. So a straight line becomes y equals mx plus c. We know that m is the gradient, c is the intercept, and as long as it's a straight line, we can pretty much find missing points, we can find gradients, we can find intercepts. Not all graphs in life are actually straight, and that's a whole new topic. There are all sorts of graphs. We notice here that this power of x has, let's say, a floaty 1. What happens if we had an equation with an x with a floaty 2, or in fact an x with a floaty 3, or an x with a floaty 4, and I think you can probably guess that this can go on. Maybe we could end up with an equation that says something like y equals x squared plus 2x minus 6, or y equals x cubed plus 2x squared minus 3x plus 4, or y equals x to the 4 plus 3x cubed minus 2x squared plus x minus 2. These are all equations and they will all give you various graphs. At this moment though, we're going to deal with this one here, which is the graph or the equations with the x squared in it, because these things here are called quadratics. Right, so there we go, an equation with x and a floaty 2, or the highest power is a floaty 2, and I mean that as in a squared, then that's a quadratic. Here is an example of a basic quadratic. It's effectively a U-shape, and it continues up to infinity and beyond on both sides. Right? Notice that nice U-curve. There's lots of things about a quadratic that are actually important to us. Let's just put some axes labels. There's y, and there's x. And this could theoretically have an equation of y equals x squared. That's the basic quadratic. That's our standard, if you want to think about it that way. What do we know? Well, we know that this point here goes through the origin. So that is the origin. The lowest point of a standard quadratic goes through the origin. And that bottom point actually has a name, and it's called the minimum. Why is it called the minimum? Because it's the lowest point. It's the minimum point, it's the lowest it goes to. It also, later on, has a name as the turning point. Why the turning point? Because it's turning. Right? Now, a lot of this has to do with gradient, and that's a much later video, in fact, a much later topic. But we need to know that the bottom of this thing here is called the turning point, or the minimum. Another great thing about this graph is, in fact, that it is symmetrical. All right? It is symmetrical around the y-axis. So points on one side, and I'm just going to draw my nice dotted line somewhere down the y-axis, it means literally it is the mirror image. This side here and this side here are exactly the same except for the x-coordinates, right? So what about our x-coordinates? What about our values? Well, if you remember the equation y is equal to x squared, what that means is for every x value you put in, the y is a square of it. So one of the points we would have, for example here, would be 1, 1. Because when x is 1, 1 squared is 1. What happens when x is 2? Well, the point becomes 4, because 2 squared is 4. When x is 3, it becomes 9, and 4 becomes 16, and so on. And what you notice is it gets steeper and steeper and steeper and steeper, because the graph numbers, when you square numbers, they get bigger. What about the other side? Well, when x is negative 1, what does y equal? 1. Really? Yeah, let's just check that. Y is equal to x, which is negative 1, squared, and hopefully you remember that a squared is you multiply it by itself. So -1 times -1 is in fact 1. Pretty cool. Let's go back to our next point. What about when x is -2? Well, again, it becomes 4. Just check. Y is equal to -2 squared, which is -2 times -2, which is in fact 4. And again, you can see that while the x values are negative, the y values all become positive. That is our standard x squared curve. Let's look at this graph here, and I'm going to put some important information in. We know that its minimum is now at the value of 2. I'm not actually going to put any other points on there, because we're just going to come up with a general idea of what happens when the standard equation is changed. This graph here would have the equation of y equals x squared plus 2. It's got that x squared on its own, and there's my plus 2. What does that plus 2 seem to do? Well, let's come back to that in a second. Let's have another example. This graph here could actually have its minimum, its turning point, at -3. What could this equation be? Well, it's the standard x squared curve that's just been moved down 3 positions, and actually it has the curve equation y equals x squared minus 3. Hold on a moment. So if we go back to our previous, when the value at the end was plus 2, the graph moves up 2 places. When the graph was -3, it moved down 3 places. And actually that's pretty true of this idea. This value here at the end is actually a vertical shift, whereby if it's a minus value, it moves down, and if it's a positive value, it moves up. Now remember, maths is a big, fat trick. So where is the trick in all of this? Well, we've looked at what happens with vertical shifts. What happens with a horizontal shift? And here is an example of just that. It's our horizontal shift. If I now write the value of the x where this is a minimum, we find out it is -4. How does that translate into our equation? Well, the equation of this is y equals x plus 4 squared. Plus 4, and this is a -4. Well, how does that work? Well, as we did a moment ago, let's go back to another example and see what happens when the graph moves the other way. Let's imagine this turning point is at a value of 3. Well, the equation of this graph becomes y equals, open brackets, x minus 3 squared. Hold on, but that's a plus 3 here, and that's a minus 3 in the brackets. We had a -4 here and a +4 in the brackets. And that's where maths tries to trick you, because it's just a trick. Yep, what we find is this value inside the brackets, the one that's with the x inside, snuggling the x in the prism with the x, is actually the horizontal translation. So that's our horizontal movement. Oh, handwriting's bad today. But it's the opposite way inside the bracket than we're expecting. So if I had the graph of y equals x plus 10 squared, we would automatically be thinking, oh, well, plus 10 will move it to the right 10 places. It actually moves the graph 10 places that way. Right? So just remember, inside the brackets is the opposite of what we were expecting. Well, what would a graph look like of y equals x minus 3 squared plus 2 then? Right? Well, we put all the graphs together, or we put our learning together, and what do we notice? Well, we've got a number outside here on its own, and previously when we had a number on its own outside of the x squared term, that was a vertical shift. Exactly the same idea. All that does is move this thing up 2 places. It moves the standard x squared curve up 2 places. And what does this value inside here do? Well, it's by the x, it's in the prism with the x, so it must do a horizontal shift, and I'm deliberately going to put 2 arrows on there, but because it's a -3, we would normally expect it to move left. This time we're actually going to move it right, because it's the opposite of what we're expecting. So actually that would move the graph 3 places that way. So do I have enough information now to put on its minimum point? Well, yes, we do, because if it's taking a standard x squared curve and it's moving it 3 places that way and 2 places up, and we knew that initially, and we know initially the turning point was 0, 0, then our new turning point, our new minimum in this case, must be 3, 2. So I can now go along to my x's. Let's pretend that's 3, and there's 2, and I now know that my new minimum point is going to be here. Well, can I find out anything else? Because maybe I would need to know where it crosses my y-axis. Yep, let's go back to a previous video very quickly and just remember that this line here is called the line x equals 0. So the y-axis is also known as the line x equals 0. So any point here can be found by letting x equal 0. We have our equation. We know that y is equal to x minus 3 squared plus 2. Well, when x is 0, y becomes, well, 0 minus 3 is minus 3 squared. It becomes 9 plus 2, or y is equal to 11. So I now know that this crosses up here at the point 11, and I can now draw a rough approximation, or more importantly, to use the right vernacular, I can sketch. It's going to look something like this. Not bad if I do say myself, even with a little bit of a shaky hand, right? So just a rough idea of drawing these graphs. Not everything in life is that easy, because maths, being a big fat trick, can throw in all sorts of different curveballs. And do all of our quadratics look like a U-shape? No. Sometimes graphs can actually be turned upside down, all right? Or they can be reflected in the x-axis. How do we know a graph has been reflected in the x-axis? Well, the x squared term is actually negative. So if there is a minus sign in front of the x squared term, then our graph looks something like this. Right? Same point going through the axis, but rather than being called a minimum, this time it's a maximum. Why is the point a maximum? Because it's the top of the curve, exactly the same. It's just a reflection in the y-axis. So that's the minus sign. How does that work with my other form? Exactly the same way. If I have a graph going y equals minus x plus 2 squared, minus 6 for example, what do I now know about that? I now know that it's not going to be an U-shape. It's not going to be a U-shape. Why? Because of that minus sign here. I know that my graph is going to look something like that, or as I call it, the N shape. Can I find the point here? Can I find its maximum point? Yes, I can. Because what do we know? Well, we know we've got this value inside with the x, which is the opposite of what I'm expecting. So plus 2 would actually move it to the left 2 places. And this minus 6 works in the right way, all right, because it's a vertical movement. And so it's going to move it down 6. Right? How else can they try and confuse us? Well, they can write the equation in a totally different form. We call this particular form y equals, let's come up with another example, x plus 4 squared minus 3. We call this the turning point form. Right? It's called the turning point form. Why? Because strangely, it gives us our turning point. There is another way of describing this, and it's called the completing the square form. All right? Completing the square form. And that was shocking spelling. All right? I'm going to abbreviate that to CTS form, and that's the basis for another video a little bit later on. What's the key point from this? Well, we've talked about maximums and minimums. We've talked about turning points, and now we know what the general shape of a quadratic looks like. And this is just the general shape of a quadratic. It's nothing more than a U-shaped graph moving around my axes. Right? Nothing more than a U-shaped graph moving around my axes. We'll move on to completing the square in the next video. Hopefully this has been of use.